right, it should be going there. Okay. So yes, we're going to continue on working on chapter 8 today. We started confidence intervals last time. We'll continue along with I'm going to review confidence intervals just briefly at the beginning of class. Then we'll talk about effect size and power. And then we will be done with chapter 8. I guess before we get started on this, does anyone have any general questions or comments, concerns about assignments, stuff like that in the course going on right now that we should talk about? All right. We can also talk after class. I think I can talk with a couple. Yeah, I can talk with people after class as well if we need to. Okay. So yes, confidence intervals. Where did we leave off last time? Just to get a brief review of confidence intervals. Here is the confidence interval that we calculated last time. Here's the two formulas. This is the this is the upper bound, lower bound, upper bound. And there's basically each one has these three components. So we have this negative 1.96 in the one that we did yesterday. We had negative 1.96 here, and we had positive 1.96 right here. That is a critical Z. And that is the critical Z that is associated with an alpha of 5%. This is the critical Z. It's a number that I've been telling you guys is an important number for us to remember because it is the critical Z, which is associated with the alpha level, which is most common in psychology, 0.05. Plus or minus 1.96 is the critical Z that marks the boundary into the critical region when alpha equals 0.05 and you have a two-tailed test. So this is an important critical Z. But I want to see if we kind of understand what's going on in a confidence interval. And so here is the diagram that I drew for this exact same confidence interval. The sample mean that we chose, 89, this was the score people on a math test after taking math drug. In a confidence interval, the sample mean is the center of your distribution. When you're doing regular hypothesis testing like we did in chapter 7, the thing that was the center of your distribution was the population mean. In a confidence interval, as illustrated here, we have negative 1.96 over here, so this is a z-score, and positive 1.96 over here, another z-score. And you can see these percentages right here that I wrote in. Each tail, this tail has 2.5%, this tail has 2.5%, which means that our alpha level, if you add up all of the percentage in the tails, is 5%. It's considered a 95% confidence interval because if we add up the amount of area in the center part, 47.5 plus 47.5, you get 95%. So this is a 95% confidence interval centered around the sample mean of 89. So something I want to think about is what happens to, how would these critical Z values changed if instead of using a confidence interval of 95%, we did a confidence interval of 99%. So we don't have to necessarily know exactly what the Z values would be, but the Z values would change. Now we're at a 95% interval, but if we performed a 99% confidence interval, the Z values would go further into the tails, even further into the tails, because if we have a 99% confidence interval in this tail, there would then be 0.5% in this tail and 0.5% in this tail. That's a 99% confidence interval. There would no longer be 5% in the two tails added together. There would only be 1% added together in the two tails, which if you divide that 1% among the two tails, that means if we're doing a 99% confidence interval, there would be 0.5% in one tail and 0.5% in the other tail. Which means that the critical Z's that we would be using for a 99% confidence interval, those would be further away from the center of the distribution. So this Z would be even more negative. It would be like negative 2 point, I don't remember off the top of my head the critical Z for alpha equals 0.05 two-tailed test, but it's like 2.3 something, negative 2.3 something, and positive 2.3 something. When you're doing the alpha equals 0.01, it pushes that critical Z even further into the tails, because the interval centered around the sample mean in the center, that gets bigger, which pushes the critical region further into the tails. That's the difference conceptually between a 95% confidence interval where the Z's are relatively closer to the center and a 99% confidence interval where the critical Z's are pushed even further into the tails. So yeah, there's our confidence interval that we did yesterday. Now we are moving on to the two last topics for this chapter, which are effect size and power, statistical power. Okay, so I'll show you some diagrams to illustrate. We're going to start first talking about effect size, and I'm going to contrast it with two things that we've been dealing with a lot now. So these three equations right here, you'll notice that they're all very similar, but they're also all slightly different. And being able to notice how these equations are similar to each other and how they're different is important to understanding the difference between them. Z-score, Z-mean, and Cohen's d. So we've worked with Z-score and Z-mean. I haven't always used these subscripts, but I'm putting score and mean here to help you differentiate between the two types of Z's that we've calculated. A Z-score is when we're making a Z-score for a single data point, a single score, a single raw score in a distribution. So that would be like a raw score, which has like a sample size of 1. And you're asking a question like how much, if you want to know a question like how much area is to the left of a score of 120, then you calculate a Z-score because you're interested in only how much area is to the left of that one score. When we're doing a Z-mean, you'll notice that this number right here is now an M. It changed from an X to an M. And what the Z-mean is, we've been dealing with this for a while. This is if you're taking a random sample of like 5 scores out of a population, you take those 5 scores out of the population, you add them together, divide by 5, you create the average. And then you want to know how much area in the distribution is to the left of this average, this mean that I just calculated. When you're doing that type of a thing, where it's more than one score, Z-score, you're just taking one score and you might have a question about percentile or the amount of area to the right. For a Z-mean, you're taking multiple scores, you're adding them together, dividing by the number of scores, you're calculating an average, and you use this formula. Another thing to notice, which is something we've been dealing with for a while, is that the Z-mean equation has this thing in the bottom. What is the name of the denominator? What is this whole thing right here called? Can someone remind me? What is this thing down here called?
Standard error.
Yes, thank you. This is the standard error versus this thing in the Z-score equation, which is just the population standard deviation. So there's really two main differences between Z-score and Z-mean. In the Z-score, this thing right here is an X, which stands for a single value. In the Z-mean, this is an M, which stands for the mean of several values greater than 1. So like 2 or greater values that are averaged together. This thing in the Z-score equation is the population standard deviation. This thing in the Z-mean equation is the standard error, which is the population standard deviation divided by the square root of n, or the square root of the sample size. So these things are similar, and we're going to learn another one today that looks similar to these other two, but it has some slight differences. And it's a measure of effect size called Cohen's d. And as said above it here, it's one of several measures of effect size, but the only one that we're going to talk about in detail in this statistics class. It measures the amount of separation between a sample mean and a population mean, and it does so in terms of standard deviation units. It does so, as mentioned here, in terms of the standard deviation of the population. So I want to kind of break down Cohen's d. It has elements that are similar to this equation, and it has elements that are similar to this equation over here. It kind of steals parts of this equation, and it steals parts of this equation, and it steals parts of this equation to give us Cohen's d, this measure of effect size. So a couple things to notice, that Cohen's d, it has M up here. So in that regard, it's close to the Z-mean equation. It's got M. So this is adding several things together, dividing by the amount of things. It's an average right here. This is a sample mean. So it's kind of like the Z-mean equation here. But unlike the Z-mean equation, Cohen's d has the population standard deviation in the bottom. So it takes the element of having a mean in the numerator from z mean, the z mean equation, and it takes the idea, the element of having the population standard deviation only in the denominator from the z-score equation over here. You kind of combine elements of each of these two types of z's, and that gives us Cohen's d. So I'll show you some more, pictures and stuff related to Cohen's d here in a second. But some conceptual things which are important about Cohen's d is that the bigger the difference in means, the bigger the difference in the means between the sample mean and the population mean, the bigger Cohen's d is going to be. And that makes sense if you just look at the Cohen's d equation. Up here in the numerator is the sample mean and the population mean. The further apart these two numbers get, the bigger the numerator, the bigger this top part of the Cohen's d equation is going to be. The further these two numbers are, the bigger the numerator of the Cohen's d equation is going to be. And as the numerator gets bigger, that causes the Cohen's d, the number that you get when you calculate Cohen's d, to get bigger as well. As the numerator increases, Cohen's d increases. The numerator increases as the difference between the sample mean and the population mean increases as well, which makes sense because we're talking about the degree of separation. The further apart the sample mean and population mean are, the further separated they are, the bigger Cohen's d, the bigger our measure of effect size is going to be. That makes some sense. Another important thing, though, is that the smaller the population standard deviation, the bigger the effect size. So this one is a tiny bit, you have to think about it just a little bit more. The numerator it seems pretty obvious. The more separated these get, the bigger Cohen's d is going to get. The denominator one we need to think about a little bit more. The smaller the population standard deviation, the bigger the effect size. So we need to think about why that would be. Cohen's d is a ratio. It's a numerator divided by a denominator. When the population standard deviation is really small, basically the smaller the denominator gets, that causes the overall ratio, the overall Cohen's d, to actually get bigger. And so this is just a property of, the numerator and denominator. When the Cohen's d is going to get bigger as the numerator gets bigger, but Cohen's d also gets bigger, but when the denominator gets smaller. Cohen's d gets bigger when the numerator gets bigger. Cohen's d gets bigger when the denominator, population standard deviation, gets smaller. Another thing which is important about Cohen's d, which is emphasized in your textbook, and I'll show you some evidence here that will supplement the textbook nicely, I believe, that measures of effect size like Cohen's d are not influenced like sample size. Z mean, because of it having the standard error in the denominator, is very much so influenced by sample size. So let's kind of look real quick at this equation right here, Z mean, and notice how it has the sample size in the denominator right here. So we have this whole thing as the denominator, and then the bottom part of the denominator part right here is the sample size. And looking at the way Z mean is structured with the standard error here in the denominator, we need to think about what happens to the size of Z mean as our sample size gets bigger. And what happens is, as the sample size gets bigger, it causes the standard error right here to get smaller. As the sample size increases, as this number n increases, the standard error gets smaller. But as the standard error gets smaller, the overall Z mean equation right here gets bigger. The overall ratio, the overall value of Z mean gets bigger. So I feel like I should say that one more time, just repeat myself. As the sample size gets bigger, the standard error gets smaller. As the standard error gets smaller, the overall Z mean gets bigger. So Z mean, and I'll show you more evidence of this in a second, Z mean gets bigger as the sample size increases. But you'll notice in the Cohen's d equation, there is no sample size below the standard deviation. There is no n in here. So Cohen's d, there is no relationship with sample sizes. As sample size gets bigger, it doesn't influence the value of Cohen's d at all. And I'll show you some more evidence of that in a second. First, I want to give you a little bit more information about what effect size is and what Cohen's d is measuring. So what we have here, here's like example A, and here's example B. And pay attention to these vertical lines right here, because those vertical lines for each example, they mark the center of one distribution. We'll pretend that this is like the sample mean distribution right here, and this is the population mean distribution right here. This is another sample mean distribution and another population mean distribution, the population distribution. And each line represents the mean of that distribution. And what we're looking at is the fact that if for one of these examples has a big effect size because the sample mean and the population mean are far apart. And in another one of the examples, we have a relatively smaller effect size because the sample mean and the population mean are relatively close together. And so this is the one up top, and you can see these two little vertical parts right here. They're close together. The centers of the two distributions, the center of the sample mean distribution, the center of the population mean distribution, they're relatively close together. So that gives us a smaller Cohen's d because the numerator of our Cohen's d would be smaller because the m and the mu are close together, which gives a small numerator, which gives a small Cohen's d. Looking down here, it's a different story though. You can see that for this example B, the mean of the sample mean and the mean of the population mean are relatively further apart, which makes the numerator of our Cohen's d bigger, which gives us an overall bigger value of Cohen's d. And so this makes sense. Like there's a bigger effect size here because the sample mean is simply further away from mu. And the further apart the sample mean and the population mean are from each other, the bigger the effect size we're going to get. So the other thing that was mentioned on the previous slide, so the previous slide says that the bigger the difference between the sample mean and mu, the bigger the effect size is going to get. That last thing we were just talking about, that concerns the numerator. Now we're going to focus in on the thing in the denominator. How does the size of the standard deviation, the thing which is in the denominator, how does this influence effect size? So please note that in these two examples now, we've controlled for the population mean. So like we've controlled for the difference between the sample mean and the population mean. So you can see the difference between the sample mean and population mean is this far right here. And it's the same, the sample mean and population mean are the same distance apart. So the degree of separation between the sample mean and population mean are the same in example A as they are in example B. That is, all these vertical lines line up here. Whereas in the previous example, you see the vertical lines don't line up. The sample and population mean are further apart in this previous example. They're close together here. In these two examples right here, all these vertical lines are completely lined up with each other. The sample mean and population mean are the same distance apart from each other here as they are here. But we notice in these examples right here that the distributions that we're looking at, these have a lot of variability, whereas these have relatively smaller variability. It's important this is something I mentioned in class previously, that you can look at a histogram, you can look at a distribution, and you can tell the size, the magnitude of the variability, the magnitude of the standard deviation, just by looking at the histogram, looking at the distribution. And the thing you can tell is that these distributions up here, they're relatively wide, whereas the distributions below, they're relatively thin. And so these down here, they have smaller standard deviation. That is, the standard deviation of the distributions down here is smaller. The standard deviation up here is relatively bigger. And so we need to consider, how will this influence effect size? So up here, the standard deviation is big. And so because standard deviation is in the denominator, when you're dividing a ratio by a big number, it causes the overall ratio to be relatively smaller. When you're dividing a ratio, when the denominator has a small number, it causes the overall ratio, the overall value of the Cohen's d, to become bigger. So Cohen's d would be bigger for this bottom example because the variability of the distributions is smaller, which causes the denominator to be smaller, which causes the overall ratio to be bigger. And if you look at these distributions, it makes sense. It kind of looks like these distributions, they're more clearly separated from each other than this top example. The mean differences between the sample mean and the population mean are the same, but they visibly down here look like the two distributions are further apart because each distribution is thinner. Each distribution has smaller variability, which makes each distribution kind of stand on its own more. There's less overlap between the two distributions. So you get bigger Cohen's d here, relatively smaller Cohen's d up here. Any questions or comments so far? Okay. So now here is the evidence. This is something he talks about in the textbook, but they don't really provide an example. So I went ahead and made up my own example that demonstrates this claim, which is made about Cohen's d, that Cohen's d is not influenced by sample size, whereas z mean, z-scores are influenced by sample size. So I want us to remember what we're contrasting here. We're contrasting this formula right here, z mean, where we're looking at how does sample size, please notice this is sample size, how does sample size influence the overall value of the z mean? Contrasting it with Cohen's d, where you notice there is no sample size in the denominator. How does increasing the sample size of our m, how does increasing the sample size of this, how does it influence Cohen's d? The claim which was made in the book, and that I've made on this slide, when I was talking about this slide as well, is that z mean, when you have a big sample size, it causes the standard error to get smaller, which causes this thing to get bigger. And Cohen's d, when you have a big sample size, because there is no n in the denominator, it has no influence at all. Sample size does not influence measures of effect size. So this is the evidence for that. I've created a very simple population. And the population shown here is the same as the population shown here. It's a small population with only 8 people, and it scores on something. I didn't even think that far ahead. It scores on a test or some type of measure of intelligence or something like that. Anything. It's just some type of score. And 8 people, and you look here, it just happens to be then the population. Everyone scored a 4 or 6. And if you add up all of these 8 scores and then divide by 8, the population mean is 5. So the mean of these 8 numbers, it's a very small population. The mean of those 8 numbers is 5. It's the same 8 numbers over here. And so the mean of this is the same population represented just again. And the mean of the population as it's shown over here would also be 5. So what we're doing from this population is over here on example A, you can see where it says right here, example A, what we're going to do is we're going to randomly pick 2 scores from this population. That will be our sample mean. So we're going to pick a sample mean over here with 2 scores, sample size n equals 2, and we'll calculate an m, a sample mean for that. And then and then we'll calculate Cohen's d and z mean. Actually, I've already done it. Cohen's d and z mean when we assume a sample size of n equals 2. And that's just plugging numbers into the formula for Cohen's d and z mean that I showed you on the previous slide, doing that for n equals 2. Over here, it's the same population, but now over here, we're going to randomly select 4 scores from this population, and we're going to calculate a mean for those 4 scores. So m, we're just assuming, by the way, I didn't actually randomly select 2 scores, and I didn't actually randomly select 4 scores. We're just going to randomly assume that when I select 2 scores, the sample mean gives us a value of 6. I randomly select 2 scores, add them together, divide by 2, and we're going to assume that I got a sample mean of 6. Over here, we pick 4 scores, add them together, divide by 4, and we're going to assume once again that when we calculate our sample mean that we get a value of 6 over here. For this example, oh, it says example A. This is supposed to be example B. I'm going to change that. Yeah, there we go. Example B right here. We got a sample size of 4 to get a sample mean of 6. In example A right here, we have a sample size of 2 to give us a sample mean of 6. And so what we're interested in is, how does the fact that we have a bigger sample size right here, how does that influence the value of Cohen's d compared to over here for 2, when the sample size was 2? How does having a sample size of 4 over here influence the z-score, the z mean, compared to over here when we have a sample size of 2? And so I went ahead and calculated all of these things. And if you want to look, by the way, I also showed you my work. So down here in the notes portions are the exact formulas that I use with the correct numbers filled in for all of these. So the Cohen's d, for example A, the Z mean, for example, A, Cohen's D, for example, mean, the Z mean, for example, mean. So all of these numbers that I calculated down here, you can find my work with the numbers put into the formulas down there in the notes portion of the slides. So now let's actually look. So when we took a sample size of 2, well, let's see if we can do the mental math. If we're calculating Cohen's D, this should be pretty simple mental math. I want someone to help me out here. If we're doing Cohen's D, recall that the numerator rather, that top half of Cohen's D is M minus mu. That is the sample mean minus the population mean. So for these two numbers right here, M minus mu, the numerator of Cohen's D would give us what?
1.
Yep, thank you, 1. And you can see that if you look in the notes portion, 6 minus 5 equals 1. I've also calculated the population standard deviation using the Excel shortcut. So you haven't calculated standard deviation by yourself in a while. I just did it for you. Population standard deviation of this population right here is 1. So the population standard deviation of this H-course is 1. So if you take the numerator, we already said 6 minus 5, that equals 1, divided by the population standard deviation of 1. 1 divided by 1 gives us our Cohen's D of 1, which is right here. Now let's go ahead and go over to this example over here. It's the exact same thing. The sample size is 4, but we get a sample mean, once again, of 6. 6 minus 5 gives us 1. So that means when we're calculating the Cohen's D over here, the numerator, the sample mean minus the population mean, 6 minus 5 is still 1. We're dealing with the same population, so the population standard deviation isn't going to change. It's still 1. 6 minus 5 gives us 1. 1 divided by the population standard deviation of 1, once again, gives us a Cohen's D of 1. So this, once again, supports the claim which is made in the textbook and the claim that I made on that earlier slide, that even though the sample size is changing, over here it's big, sample size of 4. Over here, the sample size is relatively smaller, sample size of 2. Cohen's D remains the same. It's the same population, both over here. The only difference is sample size is bigger over here, sample size is relatively smaller over here. Cohen's D in both cases is 1. Picking a bigger sample size does not influence the magnitude of Cohen's D. However, there's a different story when we're talking about Z mean. There's a different story for sure when we're talking about Z mean. So when we're talking about Z mean, though, the numerator is actually the same. And I want to verify this by looking here. The numerator, M minus mu, is what it was for Z mean, just as it was M minus mu for Cohen's D. So the numerator is the exact same. So when we're calculating Z mean right here, the numerator, the top part of the ratio is 6 minus 5. It's 1 again. The numerator is just 1. But remember, for Z mean, you're not dividing by population standard deviation. You're dividing by the standard error. And so I've calculated the standard error, which is, by the way, the standard error is the population standard deviation 1 divided by the square root of 2. 1 divided by the square root of 2 gives you this long decimal number right here. 1 divided by the square root of the sample size, which is 2. Population standard deviation 1 divided by the square root of 2 gives you this number right here. And so remember, I already said the numerator of our Z mean is 6 minus 5. It's 1. But we're going to be dividing by this number right here. 1 divided by this number right here gives you this Z-score right here. So when our sample size is 2, given the sample mean, population mean, and standard deviation, standard error, when our sample size is 2, our Z-score is 1.414 approximately. Now we're going to go over to the other example over here where we have a sample size of 4. And you notice how the standard error has changed. The standard error has gotten smaller. Why has the standard error gotten smaller over here? I need someone to tell me, why has the standard error, why is it smaller over here than it was over here?
Because N is bigger and is 4 instead of 2.
Thank you. Exactly. N is bigger. It's now 4 instead of 2. So I think we could even do this. Actually, maybe I'll show you the formula here. So we're talking about the Z mean, for example, B. The numerator is still 6 minus 5. Looking down here, I'm trying to highlight it. 6 is the sample mean minus 5, which is the population mean. So the numerator is still 1. But now we're dividing by the standard error, and it says the standard error is 0.5. Let's make sure we understand why the standard error is 0.5. If you recall, the standard error is the population standard deviation divided by the square root of n. Our population standard deviation was 1. The square root of n, so the square root of 4 would be 2. So the population standard deviation divided by the square root of 4, which is 2, 1 divided by 2 equals 1/2 right there. 1 divided by 2 gives us a standard error of 1/2. And we'll remember what I mentioned earlier. When the standard error gets smaller, the standard error, which is the denominator of our z-mean equation, when that number gets smaller, the overall z ratio gets bigger. When the denominator gets smaller, the overall thing gets bigger, and that's exactly what we see here. When the sample size increases to 4, even though the numerator is the same, 6, 5, 6, 5, the numerator is the same, the z-mean number actually gets bigger when the sample size increases. When there's n equals 4, the z value that we get is 2. When the sample size is only 2, right here rather, the z value is relatively smaller. So this once again reinforces this idea that when we're calculating z-mean, we're calculating z for a mean, as the sample size increases, z tends to increase as well. But when we're calculating Cohen's d, as the sample size increases, that has no influence on Cohen's d. So here's conventions for effect size, like what is considered a big effect size. These, in my opinion, these words right here, they're kind of arbitrary, and so I think this is of small importance overall in the big scheme of things. So these are the Cohen's d levels right here. But the reason that I'm highlighting this on the slides is because I know that there's a question on test number 3 where it gives you an effect size and you have to calculate it, or you have to determine, is the effect size in this problem, is it small, medium, large, or completely negligible? And by the way, an effect size is considered completely negligible, at least based on these conventions, if it's less than 0.2. 0.2 is considered a small effect size. If you have a Cohen's d which is less than 0.2, then it's considered a negligibly small effect size. And I think I wrote that in the notes. Yeah, an effect size below 0.2 is so small it is negligible. And I want to point out one more thing about Cohen's d, is that basically these numbers right here, Cohen's d represents the amount of separation between the sample mean and the population in standard deviation units. So if the number right here, if you get a Cohen's d of 0.8, what that means is that the amount of separation between the sample mean and the population is 0.8 of one standard deviation. If you get a Cohen's d of 0.2, what that means is that the sample mean and population are separated by 0.2 of a standard deviation. Whatever your Cohen's d is, that represents the amount of standard deviations difference there is between your sample mean and your population mean. All right, statistical power is the last thing we're going to talk about here. And so I'm really teaching to the test here. Just about every single slide that we're going to talk about regarding statistical power, the reason I'm choosing to talk about it is because I know that there's going to be questions related to this aspect of statistical power on test number 3, including this exact definition right here. There's definitely a question where you have to know this definition. You have to know, like, basically verbatim, this definition of statistical power on test number 3. The probability of rejecting the null hypothesis given that the null hypothesis is false. So this type of wording can oftentimes confuse me even, and lots of people. And so I wanted us to make sure, I kind of reworded it here to give like more down-to-earth language. You could also think of statistical power as the probability that we find a significant effect when the effect is real. And what I mean in real is like, if in reality we should find the effect, like the phenomenon that we're studying, the phenomenon actually is real. It's a real life scientific phenomenon that exists in reality. Sometimes you'll do a study on an effect that's real, but just because of random chance, sometimes there'll be an effect which is real, but because of random chance, your statistical analysis will say, no, there is not a statistically significant effect. Sometimes that happens. It kind of sucks when it does, because most of the time you will find a significant difference if if the phenomenon you're studying is real. But sometimes, just because of chance fluctuations, you'll collect data, and a small proportion of the time it's going to say, well, actually there's no significant difference between the two means that you are comparing here. And so that would be an example of a false negative. A false negative is when, in reality, you should find a difference because the phenomenon is real, but because of chance probability, because of statistical fluctuations, your data don't reveal a significant effect. Statistical power, once again, then, is the probability that we find a statistically significant effect. That is, we find a difference, we reject the null hypothesis, rejecting the null hypothesis, given that the effect is real. So we reject the null hypothesis. We find a statistically significant effect when we should find a statistically significant effect. So even another way of saying this is the probability that we will avoid a false negative. So these three things basically are all saying the exact same thing. This is the general definition, and then these are kind of rewording the definition in different ways, giving more down-to-earth language. Just to remind you, a false negative, I believe the language is in the book. They don't use the word false negative when they're talking about statistical power. They call it a type 2 error, which I just think the language of false negative is a little bit easier, because you see type 2 error and you're like, oh, what does that mean again? Type 2 error means false negative. The probability that we will avoid a false positive or a type 2 error is also what statistical power is. So the book talks about 5 factors that affect statistical power, but I'm just not going to talk about all 5 factors. I'm only going to talk about 2 of them. They're the 2 most important, arguably. The magnitude of alpha and the sample size both influence statistical power. So if you remember, our alpha level, for instance, the alpha level, which is common in psychology, is 5%, which means that in our 2 tails of our distribution, if you add the amount of area in those 2 tails, there'll be 5% of the total distribution will be in those 2 tails. If we increase alpha, then that means that the critical region, which is what those tails are, actually gets bigger. If we increase alpha to 10%, what that means is we're moving those critical Z boundaries closer towards the center of our distribution, which makes the tails bigger. Instead of just being 5% in the tails, now 10% of the distribution is in the tails. If those critical regions get bigger, remember those critical regions are the parts of the distribution where if our sample mean falls into the critical region, we conclude, yeah, there's a statistically significant effect. So if we increase alpha, we make those critical regions bigger, we're increasing the likelihood that we find a statistically significant effect. So increasing alpha, making it bigger number than 5%, like 10% or 15%, that increases the likelihood that you're going to find a statistically significant effect. So that's one way of increasing statistical power. Increasing alpha increases statistical power. Changing sample size is the other way that you can influence statistical power. And so the reason is that increasing sample size decreases standard error. We've already talked about this when we were talking about the Z mean earlier. The square root of n is part of that standard error equation. As the square root of n gets bigger, the overall standard error gets smaller. As the standard error gets smaller, this makes the overall Z that you're calculating bigger. The bigger that overall Z that you're calculating gets, the bigger it gets. That means the further from Z equals 0 it's getting. That means the more into the tails the Z is getting. The further into the tails our Z is going, the more likely we are to find a statistically significant effect. That is, the more likely we are to reject the null hypothesis. Any questions or comments about statistical power? So that's all I have plans for today. I am happy to stick around and ask questions. I'll probably stop recording now.